Let's thank Ban once again. And now I invite Bruno.
First and foremost, I would like to thank the organizers, Sanathan TRG, most of all because of the problems that they faced. Hopefully, they're all behind us. And I would like to, well, give happy birthday to the person in charge. We've been known each other for like 30 years now. It's a long time, and we'll be discussing much physics. Bal has been a beacon of light at some points during my career, and I'm glad I count him as a friend. And I was asked yesterday what I'm doing here because I've never been to room 316, and I've never been to Syracuse actually. But I think I traveled this way to say happy birthday and to hopefully have some nice conversations. Not all about Brazilian politics, I hope. All right, so I guess I will start with the actual physics. I'm going to talk about some work I've been doing in the past years, and I see this basically as a combination of the ideas I've been following through, and most of them are in mathematical physics. So I guess I have to apologize a little bit to the audience. But I hope with some patience, I guess I get to some physics by the end of it. Anyway, this is the outline of the course. Sorry, of the seminar. It is. I will start with some well-known facts about CFT. I mean, there are some things that I need to remind myself. I needed to remind myself, and I ask again for patience for people that are in the known. Hopefully, that will set the language. There is an alternative take on this mathematical structures. I'll be going through, basically having to do some nice mathematics from 100 years ago, but they came back in shape from 2013 to recently. And I'll be talking specifically about the problems or mathematical problems I need to be looking at in this fourth section. In the end, hopefully, I will take some time and talk about the physical applications. Most of them have to do with black holes, quasi-normal modes, but we will see that it's a bit more ample than that, and hopefully a bit more useful than just that application. Anyway, I would be remiss if I didn't talk about my collaborators. This has been working. I've been working on this for some years now, especially with Fábio Novaes, who's now a faculty back in Brazil. Juan Barragan Amado is a postdoc in Korea. I forgot the name of the university. Tiago, unfortunately, had to flee academia because he couldn't land a job. Things in Brazil were not looking right at his time. And João is the major collaborator here, and he'll be looking for jobs soon. So I guess that perhaps you'll hear more from him. The people in the second line are basically already seniors, and Elisabetta is at Groningen in the Netherlands, and Rodri and Darren are at Imperial College London. Anyway, let's start. I guess everybody here knows about CFTs. Basically, theories in which you have a extension, if you will, of Poincare invariance, and in which I'm allowed to make different homospheres as long as they keep scales invariant. So I want to preserve angles, and that's where the conformal bit comes from. I will be particularly interested in so-called primary operators. These are operators which have this particularly nice transformation law. So they basically transform as a power of the Jacobian, so a power of the volume element. It's a well-known fact that CFTs, the fact that you have extra symmetries, not only Poincare would be a subcase in which this function here is 1. Or isometries actually would be phi equals 0, but anyway, the fact that you have this extra symmetry allows you to fix 2 and 3 point functions of any primary operator. So here is the particular example for 2 point functions and the example for 3 point functions. And if you are more algebraically minded, you will see that there is some structure that's screaming itself here. You can see these 2 point functions as some inner product between operators, so primary operators. This is called the BPZ, inner product of this the operator algebra, and the 3 point function gives a sort of structure constant. So this will be important for the so-called conformal bootstrap program. This is one of the major achievements of 1980s theoretical physics, in my opinion. The BPZ paper, 1984, I think, talking generally about systems near criticality. They're like Ising model at the critical temperature or string theory. Right, 2 dimensions, things actually get much interesting because you get from just an extension of the Poincare algebra into a full-fledged infinite dimensional symmetry algebra. It's called the Virasoro algebra, and it has this defining commutation property. And you see here that the algebras are parameterized by this number C. It's called the central charge. The major problem of the conformal bootstrap in 2 dimensions is actually to understand which type or which values for the central charge will give you a sensible theory. We will talk a little bit more about this, and you can construct from the algebra the highest weight representations, just like you do in angular momentum studies in quantum mechanics. You construct this primary states, which are just the action of the primary operators into the generic, in this case, SL2C invariant state. They are annihilated by the sum of half of the Virasoro generators. The BPZ dual is given by this. I mean, this this gives the proper or the more natural normalization of the state in 2 dimensions. And you have descendants, which are the analogs of the creation operators being acted upon on this state. So this generically will give you some level given by n, the capital N, on the lowest lying state on the spectrum. The terminology lowest lying and level comes from the fact that this state, you can work out using the algebra that this state is an eigenvalue of L0, which plays a role of the Hamiltonian in this case. More importantly, if you assume that this pairing is orthogonal, you can compute the inner product just from the Virasoro algebra, and generically from level n, you get matrix of inner products between the states. It's called the Katz-Shapovalov matrix. And studying these eigenvalues of this matrix allow you to establish whether the theory that you are trying to define is unitary or not. Again, this will come in handy pretty soon. I talked to you about 2 and 3 point functions. 4 point functions is a bit more complicated, but you still can use the conformal symmetry to your help. So the way you usually do that is that you can, well, first of all, you can use global conformal symmetry to fix the coordinate dependence of 4 point functions. So in the end of the day, you have a single conformal modulus T there as an independent variable. And you can use the OPE to decompose the product between 2 operators into primaries. Different primaries, I'm labeling these primaries here by P, and generically you're going to have some operators here which can be a primary operator if you are in the lowest lying part of the decomposition, but you can also have descendants. In the end of the day, this point here is just the action of this projectional operator into this the states constructed in this primary. It's called Velma module usually. And you have some structure constants there, and you have this dependence with T. The important bit for us is that these operators that you have here, all the sum of them, they are analytic with respect to t. So the no-analytic part is completely encoded in this leading term here. And then by using this and the pairing between the primary operators, the BPZ pairing from this, you can basically write the 4-point functions with this fixing as a sum of intermediate channels P, Vema modules labeled by P, with this leading factor, which is non-analytic, and a particular function here, which is analytic in T. This function, I'm using the script alpha here. This should be T, by the way. It's completely determined from the conformal algebra. So in the end of the day, it only depends on the particular representation of Virasoro algebra you're studying. These are called conformal blocks. So these are the building blocks for higher point functions in two-dimensional CFT. Usually, you represent those by this tree diagram here. And in this particular case, I'm considering t between 0 and 1, but generically, you would like to know what these functions look like for generic values of t. Okay. Now, I'm going to motivate you on the physical aspects of this later on, but so far, I'm a bit more interested in the mathematical part of it. How to define this function? What are the global properties of it? So first thing you have to work out is, okay, I define this function using this procedure here, which is fine, but I have to work out the expansion. Knowing the expansion is not knowing the function. So in principle, I can use some other scheme to decompose this, the 4-point function, and have an expansion at a different singular point. For instance, in this case here, I'm choosing to decompose the OPE between these two operators from 0. So obviously, you're going to have some factor here of t. So you're going to have problems when t comes to 0. So that's where you expect this non-analytic behavior. But you might as well think, okay, so perhaps a value of t is closer to 1 in the sense that it makes more physical sense to do the OPE between these two operators, the one sitting at 1, the one sitting at t, before considering the rest of the product. And that will give you naturally an expansion around t equals 1. If you choose to large values of t, it would make sense to make the OPE between these two operators here. So that would make you, give you, in the end of the day, a expansion around t equals infinity. So you see, there is some analog here between two particle scattering, usually in usual quantum field theory, in which you have some sort of S channel, which I'm drawing here, but you can also have some sort of T channel when t is close to 1, and some U channel when t is close to infinity. This will give you different expansions of the same 4-point function. And these expansions are related by what is called in CFT fusion rules. But it's not clear how to compute them efficiently, especially not at general values of the central charge. The expansions themselves can be computed using a variety of methods. The method I've just presented to you is the most straightforward one, but it's also very slow. It's actually not very useful for practical purposes like the one I'm going to present by the end of the talk. But you also have some different approaches, which are actually very interesting. Unfortunately, I won't have much time to go through them. One of them is using Nekrasov functions, and that comes from the AGT correspondence. In strange turn of events, you can actually show, and this has been proved already, that these conformal blocks, they actually can be written as instanton partition functions of n equals 2 super Young Mills in 4 dimensions, which is rather strange and hard to understand. But anyway, that's how it pans out. It's not only super Young Mills, you have some matter multiplets. The matter multiplets actually give you the relation or the dependence with these conformal dimensions, these deltas here. You can write genetically these expansions. They work very well in the sense that you have nice Taylor expansions type of expansions for the conformal block, but they are a bit slow in the sense that it's very hard. They take exponential time to actually compute, so it's not really efficient in the sense that I'm talk about this here. On the other hand, there is one added bonus when you try to relate that to super Young Mills, is that you can use all the machinery that people have been working in flat connections in 4 dimensions and try to understand what do they mean in CFT language. In particular, you have this so-called blow-up formulas, and this comes because some of these partition functions or some of the path integrals we use to define this n equals 2 super Young Mills, they localize the sense that the semi-classical approximation give you the exact result. They actually relate, they make deep statements about the representation of Virasoro algebra for different values of C. I won't have time to go over that, unfortunately, but there's a one single consequence of that fact that will be very useful to us. You might at this point say, okay, this is all well and fine, but why exactly are you boring us with all these technical details? Well, this slide, with some hope, will clear some of the problems. When you study the matrix, this matrix of inner products I talked to you about earlier, you find that you have a polynomial, I mean, as you expect, and the polynomial will depend on the dimensions of the primaries at level n, and this polynomial will have these roots here, which are labeled by 2 known negative integers, m and n. I'm doing a slightly different parameterization of the central charge here using this B and B inverse. I'll be telling more about that in a later slide. But I just want to show that there is a level 2, for instance, as a particular example of this. You're going to have a state which has 0 length in the representation of the theory. So if you choose a particular primary, you can show that this descendant from this primary will have 0 length. So if the theory does make any sense, this vector or this state has to decouple from the rest of the theory. That's what's called a null vector. This null vector, well, you can sort of pair that with the rest of some other primaries, and the OPE between these Virasoro generators and the rest of the primaries will give you what is called conformal word identity. There is a partial differential equation in this case that is satisfied by this correlation function, and the correlation function involves regular primaries and capital N regular primaries here, and this particular degenerate primary associated to this state. This equation, which I'll be calling conformal word identity, is called level 2 identity, some other names in the literature. It is quite important to us for the application. So I would spend some time looking at this right now. I guess this should be K21 to N, but anyway. You see here that there's a second order in Z, and it's first order in each of the positions. So Z here is the position of the degenerate operator, and ZK are the positions of this other primary operators. What is usually studied, and what will be particularly useful to us, is to study this conformal word identity in the semi-classical limit. What do I mean by that? Well, the B parameterization that I just showed you in the last slide is related to the central charge by this formula. Usually, this Q here is a proper way to parameterize the Liouville theory, which is the theory of representations of the Virasoro algebra, and B here is a nice way to parameterize the null states. You can see here from the theory of the Liouville field theory, B sometimes has the interpretation of H bar. B square actually has the interpretation of H bar. So what do I mean by classical limit is to take B equal to 0. You see here that there is some values. B equals 0 is formally the same as B equals infinity. You just change some of the degenerate operators, so it doesn't make that much of a difference. And the other point I would like to B can be in general a complex number. You don't need that to be real. So you can have, for instance, B equals I. When B equals I, you have C equals 1. And that's a particular point in the theory of Liouville that will also be interesting to us. If you work out the conformal dimension, then by taking the semi-classical limit, I would like to take the conformal dimension to be large as well. So the B equals 0 will have the conformal dimension going off to infinity in the scaling factor. And I'll be wanting to have also this intermediate conformal dimension to be semi-classical. And it's a fact. It's one of those things that nobody seems to be able to prove. Although there was a claim proof by Per Krauss 3 years or 4 years ago that the conformal block, as I just defined earlier, exponentiates. So you can write that as the exponential of 1 over h bar of the semi-classical action. And this W, script W there, it's what we'll be calling the semi-classical conformal block. This factor here is not so surprising if you think that in the semi-classical limit, the 4-point function should be given by basically the classical action. And if I told you, if you believe me, that B squared has the role of h bar, this somehow makes sense. But it seems like something that's completely non-trivial to prove. But anyway, these people have claimed that, these people from LA have claimed that they proved that, but I'm not sure this qualifies. B? Not really. I will be looking at this. I am interested in unitarity, but this will come an afterthought here, because I'll be doing everything sort of algebraically. I'll be coming back to that. Right, and when delta is negative, for instance, I can understand that as sort of the out vector, not the in vector. I don't need the. I mean, it's a bit more subtle. Anyway, also the important factor here for the physicist point of view is that when you have the semi-classical limit, I mean, these deltas, they are large numbers, regardless positive or negative. So, but on the other hand, this remains finite. The dimension of this remains finite. So in a sense, these are heavy operators in which you are perturbing by using an operator that's particularly light compared to this one. So you can understand that the correlation function will factorize. Here you get this the conformal block from this point here. So this comes as semi-classical factor, and over this background, the fluctuations that will be completely associated to the degenerate operator. So you have some kind of wave function here that will depend on the positions of these operators, but the position of this operator, of course, won't suffer any back reaction from the position of this one because this is light. If you do that, I mean, if you do this factorization here, then it's a simple matter to go back to this conformal word identity that I wrote down here, and show that the psi, this wave function, actually satisfies a ordinary differential equation. So this point here becomes a function which is independent of z. And on top of being ordinary differential equation, is also a differential equation of Fuchsian type, meaning that you don't have any essential singularities. You only have regular singularities. And of course, I'm telling you the story backwards. Liouville theory usually is a way to think about this Fuchsian differential equations as a classical limit, and Liouville theory itself as a quantum version of this classical properties. The important bit to us is that the classical, and I call it T here for a good reason, because this has the classical interpretation of the stress energy tensor of the CFT. The parameters in this T here are related to the analytic structure of the wave function. So there is a relation here in which these accessory parameters, they solve the original form of the Riemann-Hilbert problem, in which you want to know how the analytic properties of this wave function depend on C, or vice versa. This is the part I'll be talking more about. You can understand that just by looking at the solutions of this ordinary differential equation. It's a second order ordinary differential equation, so you can solve that using methods that you learn in mathematical physics first course, Frobenius methods, for instance. So you know generically that you have two solutions. You will know that each of the solutions will have a strange behavior in which you're going to have a leading part. This solves the initial equation that contains the non-analytic behavior near zk, and a part which can be expanded near zk. So it's analytic in z near zk by definition. And you have two of those. Why do you have two of those? Well, this is something I'm going to come back later, but you see that if you think of these now as generic functions in the complex plane, the leading part here will tell you how this analytic behavior near zk is. For instance, if you go around the singularity at zk once, if you take the degenerate operator around zk once, you're going to have a factor coming from this and a different factor coming from this bit here. These terms are analytic and they won't contribute to the solution. So each of the solutions will pick up a phase. In this case, this theta here are the classical version of the Liouville momentum, and they can be complex numbers. At least there is a solution for generic complex numbers. Right. The solutions that I just wrote to you, just explained to you, they are called Frobenius solutions of the differential equation. And as I tried to explain to you before, these Frobenius solutions, there are two of them. They correspond to the OPE. That means the product expansion between the degenerate operator and the non-degenerate operator. So what does that mean? I have 10 minutes. Okay, I'll be try to be fast. This here corresponds exactly to the OPE between this degenerate operator, this non-degenerate operator. Here you see a family with this particular primary operator, this also family with a different primary operator. You also have what is called Floquet solutions. And this corresponds to the OPE between the degenerate operator and the intermediate channel. So you see that what I'm doing here is basically try to translate the CFT language to the usual classical differential equation, ordinary differential equation in the complex plane language. There are expansions of these conformal blocks, these W's that can be determined using particular techniques. I'll be showing them hopefully soon. And how they relate, it's a bit more complicated. But anyway, the particular solution, the solution that you have for that, they should encode the monodromy structure of the wave function. And the monodromy structure of the wave function relates the parameters in the differential equation to the analytic structure of the solutions. Okay. I guess I don't need to go into that really. I just wanted to point out that this monodromy matrix here shows how to relate the solutions after you go around one of the singularities once. There are four of those, in the case where there are four of those primary operators, you're going to have four of those matrices, and they all multiply to the identity matrix, because if you go around all the four of them, you're going to have a contractible curve. If you work out the number of parameters you have to determine these matrices here, you're going to have exactly two parameters. This will be important soon. Right. Nice way to encode the monodromy structure, these two parameters, is to define this differential Nielsen coordinates. In this particular channel here, I'm looking at this S channel. It's nice to talk about the trace of the product between the monodromy around two of the primary operators, and this zeta parameter here, which corresponds to the twist between these two primary operators as you glue them together to make the two different ones. So in a way, you can think of that as a complex plane between, and then you consider a circle that's encircling two of the primary operators. You have two in the exterior, and before you glue the two of them in the CFT sense, you rotate one of them a little bit. This is the the geometrical interpretation of this zeta variable. Well, there is a symplectic structure behind this. You can show that in the symplectic structure, it's called in this case the Goldman bracket. I won't have time to go over that, but I can explain to you if you are interested. These two coordinates, sigma and eta, they are conjugate. And so the fact that it's a very complicated dependence here is somehow forgiven, since you can think of them as double coordinates to each other. So in the sense, eta is simpler than the. And as I told you, the Riemann-Hilbert map relates these monodromy coordinates to parameters in the differential equation. So the symplectic structure of these coordinates are translated to the symplectic structure on the differential equation. And lo and behold, the two parameters in the differential equation, which are not set immediately by Frobenius analysis, they are also canonically conjugated in this language. So the map between these two can be thought of as a symplectic map. Right. Actually, computing them is not so difficult. This has been known for some time, I guess since the 30s. There is a very fast computational method using continued fractions. I won't have time to go over that. And then you can try from the relation, there should be a log here, but from this relation, you can try to integrate and find W from the accessory parameter. And this equation here gives the accessory parameter in terms of monodromy data. So you find an expansion like this as a function of t, and before you try to find the eta parameter, you have to find the integration function in terms of sigma. It is independent of t. There is a way to do that. I'll be going over soon. Well, the way to do that is actually to relate this to isomonodromic problem. I won't have time to do that, but you can, using some other methods, you can relate the accessory parameter to the log derivative of this so-called tau function. And the conjecture you're putting forward here, there are some conditions on the tau function anyway, but the conjecture I'll put forward here is that this bit here is essentially the W, the thing that I want to compute. If you do that, you can solve things. So this is what's important to us. But it's also interesting to note that the expansion of the tau function has been found out by these people from Ukraine. Well, one of them is a French citizen now. That they are related to C equals 1 conformal blocks. So this is one of the consequences of this blow-up formula, because I told you before that the C is given by the semi-classical conformal block that comes when C equals infinity, and here you can state this function in terms of C equals 1 conformal blocks. And I don't think that's this relation is really understood, but it's there. The important part about phrasing that in terms of C equals 1 is that you can use global structure of this tau function to define the C globally in the complex space, not as just expansion, but in the whole complex, the whole Riemann sphere. So you can use action of the braid group in the tau function. You remember, this is a tau function associated to a sphere with 4 punctures. So you have a natural action of the braid group there in order to get relate expansions around different singular points. And from there, you can find this F function that was not known before. Right. Just quickly going through the rest, you can repeat the same arguments for t equals 1 and t equals infinity. You're going to have different expansions. And because you can recover the monodromy structure, you can compute this eta associated to this sigma values for each one of these channels. So you have a sort of S channel, T channel, and U channel, but you can compute sigma and eta U and sigma U with knowledge of these alone. So using that, you can relate expansions at different points. So you can define this W globally. in the all Riemann sphere. I'm using this almost equality here because they are the same up to sigma and t invariant terms. So in the end, you're covering the Riemann sphere with these three patches, and so you are able to compute this function globally. Anyway, same thing works for confluent limits of the differential equation. I'm going to say that. Not going to go this, but I'm going directly to the application. The 2 minutes I have left. Sorry. When you're computing linear perturbation of four-dimensional Kerr black holes, you're going to find two coupling equations. These are the so-called Tolkowsky master equations in vacuum. And it's a small wonder that they are separable, but we are not going to go into that. I'm just going to show that despite this being very ugly and very complicated, these are all instances of the confluent point equation. And I'm going to use the machinery I just presented to you to try to solve some problems related to these equations. Which type of problems? Well, I told you that I have a way to relate the parameters in the equations to the monodromy of the solutions. And it just so happens that the problems that I'm usually interested in when I write down these equations, quasi-normal modes and scattering problems, they are expressible in terms of monodromy conditions. So just to give you an example, if you want to find the angular angle value, you just need that this sigma parameter, monodromy parameter, to be related to the theta monodromy parameters by an integer, in this case, an even integer. If you apply this directly to the equations, you can read the parameters from just phrasing the equation in this in the standard form that I listed before. You can easily compute these expansions of low frequency expansions of the spheroidal harmonics. So this is an expansion A omega. And by using this global structure, you can also compute the expansions at large frequencies. So this should be a -4 here. So the expansion of large frequencies also depend on the monodromy parameter. In this case, I'm calling it eta, just to add to confusion. But you can also compute that procedurally without any problems. Any computer algebra system will do that in seconds. It's surprising analytic, by the way. And although the solutions, they are non-analytic near infinity because they have this exponential behavior, the eigenvalues are. The radial equation is more interesting. There is an irregular singular point at infinity. There are regular singular points at the horizons. This theta parameter that is related to the real view momentum and also to the scaling behavior near R plus and R minus has this structure. The smart people among you will recognize this as the entropy intake of the horizon, as it acquires a quantum of energy omega and moment angular m. But you have an integer part, so this is not exactly unitary. If S was 0, then this would be unitary. The fact that it's unitary even for f equals 0 is also a small wonder. But anyway, the interpretation at infinity is a bit more complicated, but you can just run the machinery. You place the boundary conditions in terms of monodromy data, so you're going to have this somewhat complicated solution. You read up the parameters from the differential equation, and then you just crank up the machine. This is just to show you how they relate to the usual methods. So we recover them easily. But more importantly, we can go over to the extremal point. So this was not something that could be done before because they didn't understand how the global structure of these expansions work. I won't have time to go over that, so I'll just skip it. You can basically write or understand the near extremal limit of all these solutions or quasi-normal modes. The funny bit is that at the extremal point, there are some quasi-normal modes which are given by the confluent limit of this equation, which is expected, but there are some quasi-normal modes which are missed. These are usually called this co-rotating limits. You can also work out the large, in this case, the large parameter expansion. This here has to do with again has to do with the frequency. So you can compute overtones. There's no problem with that, using the larger expansion. And you can understand how the analytic structure of the overtones, they depend, well, in this case, how they behave in the complex plane. And the funny bit that, just to show you that there is some complex structure going on, the fact there are these non-rotating modes or co-rotating modes in which L equals M, and the imaginary part of the quasi-normal mode frequency goes to 0 as you go closer to the extremal limit. In this case, is L equals 2. But you see that for the overtone 1, 2, 3, 4, 5, it goes to 0, but for n equals 6, it doesn't. It goes backwards. So there is some complex structure here, which is not easily understood, but at least you can get there. Anyway, I'm finished. I hope you got something out of it. Just try to show you that understanding these global structures of these conformal blocks are important for CFT for sure, but they're also important for the kind of problems that I'm considering here. We have some practical purpose. We want to compute these quasi-normal modes in a way that's efficient. So you can tell these people, look, I mean, we can do that. And there are some analytic expansions that are useful, sure, but you can put that in computer if you want to and crunch some numbers. There is this thing about the unitarity. It's something that I've been questioning myself. Should you take this chiral CFT that you get seriously? Because there is apparently there is some structure there which is not quite understood. All I have to say is that's nothing to do with the chiral CFT that people propose for black hole parameter that people discussed 2 days ago. It's not there. For one, there is some funny thing coming on in the guise of the spheroidal harmonics eigenvalue. If you look here at the differential equation, both of the equations depend on this the angular eigenvalue. So in a sense, this has to be computed from the angular equation, then fed into the radial equation. If you remember that the accessory parameter, in this case the lambda, is related to the logarithm derivative of the tau function. So you have an expression that's roughly the fact that the eigenvalue that show up in the angular equation is equal to the eigenvalue that show up in the radial equation means that the log derivative of this angular eigenfunction is the log derivative of the radial tau function. If I show you some people that work on integrable systems, people that have contact with tau functions besides this property, they will tell me that this is an equilibrium condition between this angular system and the radial system. I don't know what that means. I wish I knew. Anyway, we have a procedural way to compute this Riemann-Hilbert map. For generic Fuchsian equation, it should be also important for many other scattering problem bound states besides what I've been discussing here. And the fact that you have these repeating expansions at different points is related to resurgence in a way that, again, I wish I could elucidate. Anyway, thank you very much. And sorry for being over time.
So we have time for 2 very short questions. T is coming up, so you can discuss at length with him. Okay.
Hey.
Am I correct in understanding that you, for arbitrary frequency, not large or small, so you reduce the differential equation to a transcendental equation, right?
Yes.
And that for arbitrary frequency, you just solve by numerical. Is that
You
correct?
can do that, yeah.
I mean, that's the only way to handle that for arbitrary frequency.
For arbitrary frequency, yes.
Okay, and that matches with calculations from numerical methods completely.
Yeah, the only thing that we added to the game is usually people have, for instance, the behavior as you go towards extremality and the behavior from extremality. We could bridge it, the both of them. There are some stories that I can tell you. I would be happy to tell you about Heiss and Nordstrom to show how these modes, they jump from this behavior between damping to non-damping. And we were, to my knowledge, the first ones to be able to do that because that needed you to understand how the global structure of these expansions they work.
Okay, thanks.
But let me just add, it's not different, for instance, if you find some problem which requires to compute the hypergeometric function at some finite point. You also need, actually, I want to defend it. It's actually the same thing here.
Okay, so let's thank.
Okay. I mean, since he's the, I would like to thank you for being such a generous person. I mean, really, really, in the sense that you always being happy to discuss physics, to help us and clarify even the problems that you are not particularly interested in. And I just found out today that it goes beyond just being scientifically generous. So I was given 300 rupees by Bal, which made me very happy. Thank you.